The structure was complete, everything passed inspection, but after the first rainfall, the outfield failed. Water didn't drain, the subgrade softened, and within hours, the ground lost its bearing capacity. That's not a design failure, that's a site execution failure. Before any drawing is approved, this is where we stand. Raw ground, unpredictable soil, and unknown risks below. What looks flat and stable on the surface can behave completely differently under load. This stage defines the entire project. We don't assume soil behavior, we measure it. Boreholes, SPT values, groundwater levels, these tell us how the ground will respond under structural loads. On real sites, ignoring soil data is one of the fastest ways to guarantee failure. Earthwork is not just excavation and leveling. It's about achieving uniform load distribution across the site. Every layer must be compacted at the correct moisture content, otherwise settlement becomes inevitable. Most early stage failures start right here. Field density testing is where theory meets reality. You're not just checking numbers, you're verifying whether the ground can actually carry the design load. On real sites, reports can look perfect, but only physical verification tells the truth. These piles transfer structural loads deep into stable strata, but execution is critical. Bore stability, slurry control, and vertical alignment must all be maintained within tight tolerances. If the base is contaminated or improperly cleaned, the pile capacity is compromised from day one. Concrete strength doesn't come from mixed design alone, it comes from proper placement and compaction. Vibration must eliminate all voids within the matrix. If air pockets remain, you're reducing strength before the structure even begins service. Precast elements improve speed and quality, but installation accuracy is non-negotiable. Even minor misalignment affects seating geometry and ultimately the spectator's line of sight. In stadium design, user experience is engineered. Steel erection at this scale is high-risk work. Load distribution, lifting sequence, and wind conditions must be continuously monitored. Steel structures don't tolerate improvisation. One uncontrolled lift can compromise the entire system. This is not simply a grass field, it's a layered engineering system designed for performance. Each layer from subgrade to root zone controls drainage, stability, and turf health. If one layer fails, the entire system fails. Drainage performance must be proven, not assumed. Water should move through the system immediately, without ponding at the surface. On real projects, inadequate filtration or slope errors lead to long-term operational failure. Keep it steady. Stadium lighting is a precision engineering system. It must meet broadcast lux levels, uniformity ratios, and eliminate shadow zones across the playing field. This is not aesthetic work, it's performance-driven infrastructure. Finishing works appear simple, but they carry schedule risk. Late design changes, coordination gaps, and procurement delays often accumulate at this stage. On real sites, many projects slip timelines right here. Before handover, every system must be validated. Structural integrity, drainage efficiency, lighting performance, all tested under real operating conditions. Because once the stadium opens, there is no margin for error. What began as raw ground is now a fully operational stadium. Every layer, every connection, every system, working together under real conditions. This is not just construction, this is coordinated engineering at scale.